Hello there. I'm Tanisha Rajgor, and my invention is a novel, efficient way to conduct deepfake detection using Haar, Cascades, and GANs. To introduce myself, I'm currently in 12th grade from Hopkinton, Massachusetts. I love tinkering and innovating with AI, especially neural networks and computer vision. Over the years, the number of deepfakes, or computer generated images, videos, and voice recordings, in circulation is increasing rapidly. Deepfakes are notoriously known for their ability to manipulate consumers, fabricating media and spreading misinformation. They can be used to impersonate individuals, especially those with influence, to enact confusion in the public, particularly those in matters of politics and the economy. The widespread global use of social media platforms such as WhatsApp, TikTok, and Twitter only aids in the propagation of such forged content. Anyone can be susceptible to stolen content and identification that could be used against them. The following slide consolidates the previous information into a problem statement. In order to mitigate this issue, media produced by deepfake generation technologies must be detected before they get the chance to circulate. Furthermore, the direct source must be combated in order to prevent initial creation. The intended market would ideally be social media companies, many of which constantly scope their platforms for inappropriate or dangerous material that violates terms or are illegal. They are on the lookout for innovative and efficient ways to keep their environments safe and welcoming. For example, Facebook recently had a deepfake detection challenge in 2020. Here are some of the current approaches used to detect deepfakes, many of which I have used conjointly in order to create a unique solution to the following problem. To simplify the detection process, videos are often broken down into singular frames. It is much more efficient to locate and verify facial features this way. Generative adversarial networks deploy two competing neural networks, producing higher quality simulated media over time. The first network, called a generator, produces fabricated images. The second network, or the discriminator, is trained to distinguish with real photographs. This approach, used singularly, can fall victim to reverse engineering. Although not directly processing media to determine authenticity, blockchain and time signatures have also been used to confirm a piece of media's date of origin and possession. The engineering design process is a multi-stage cyclical workflow pattern used in defining problems, prototyping, and testing solutions. I will briefly cover my journey and what I learned throughout this process. And more detail and documentation can be found in my invention log. I've color-coded the different stages in the log to showcase my steps more clearly. I broke up the final desired outcome, which was a combination of the previously outlined methods, into smaller phases. These arose from extensively brainstorming and analyzing possible solutions and their pros and cons. For the best security and efficiency, Haar cascades will be used for initial face recognition, and GANs will be used for checking authenticity. Once the problem and possible solutions are defined, I introduced specific performance criteria or objectives that I'd like those solutions to accomplish. We will primarily be focusing on phase one and phase two. Phase one consisted of analyzing still frames or images, in a sense, of fabricated and genuine video in order to pinpoint key facial points, which in turn helped detect the location of the entire face. These additional facial features included the eyes, mouth, nose, using different classifiers for each one. Fabricated images were sampled from Google's Deepfake dataset containing 3,000 fabricated videos. ArtBreeder was also used to generate media, being able to specify factors such as ethnicity, age, gender, and hair types. In the algorithm I developed, each image is broken down into several smaller blocks. For each facial feature, different cascades perform calculation on adjacent rectangular regions at a specific location in the detection window. The calculation involves summing the pixel intensities in each region and calculating the differences between the sums. This creates a histogram of oriented gradients, sort of like a map of the image. The following is a sample of some of the results from testing different categories of images. The younger the age of the individual in the photo, the more likely that the model was able to detect more regions where the eyes can be located. The mouth and the nose classifiers were not as accurate as the face and the eye classifiers. Hair seems to confuse the model, mainly in thinking that it could be an eye region. After this initial testing round, more classifiers were added such as hair and eyebrows. Phase 2 takes the facial feature recognition onto a bigger sample size of 2,000 images. The unique combination with MesoNet assigns a confidence value to each prediction, with 100% meaning an input is completely genuine. The following recaps testing analysis and elaborates on the target market. The next steps include the addition of phase 3, which was implementing the detection algorithms to video. And this requires more attention to overall trends, such as audio and lighting. With prospects of market expansion, currently the model is in a form of a computer program or a Jupyter notebook. This one we use Google Colab, and this is primarily used in industrial settings. The technology could be integrated as a mobile application in order to facilitate personal use. GANs are often also used to help create personalized voices for those that suffer from conditions such as ALS, aiding them in communication. Thank you for listening.